In the last lecture, we stopped on this slide, which says what are the relative volatilities for equal cost separators. So if we start on the x-axis, looking at ordinary distillation, and we say, well, if we've got for a certain separation, we've got an alpha, a relative volatility of 1.4, how much must the relative volatility be in extractive distillation for it to be financially viable to rather do extractive distillation? So here's an equal cost separation. We would need approximately 1.9 of the relative volatility of ordinary distillation. We have to move from 1.4 up to about 1.9 with the extractive distillation to make it viable or financially viable to use extractive distillation. So let's just get a line. In yellow. Excuse me while I enjoy my game here. All right, let's put that right up to 1.4. Right, so for extractive distillation to be equal cost, you would need at least an alpha of 1.9. And then with liquid extraction, of course, you can't use relative volatilities because it's a liquid equilibrium that we're talking about. And for that, we would need to go, let me choose line again. I think we've got a line, so we can go across here. And it would need to be, what's that? 2, 3, 4, 4.9 to make it a viable, to make it an equal cost separation. So if we've got a beta of 10, of course it would make financial sense to use liquid extraction if it's 10 instead of 1.4 for ordinary distillation. So that's essentially how you use this this graph, and it allows you to choose whether you're going to do ordinary distillation or extractive distillation. Extractive distillation is that example where we use furfural to help extract butene, and liquid extraction is an example where you have an organic mixture that contains an alcohol. If you add water to that mixture, the alcohol will preferably dissolve in the water. And because it's water, it is very polar, and you will have two different liquid phases, with the alcohol preferably going into the aqueous phase. So that's what this graph is all about. Right. So generally, you will use ordinary distillation to make your separations. So use of the sequence of ordinary distillation columns, or use a sequence of ordinary distillation columns, provided the alpha in each column is greater than 1.05. So when it gets less than 1.05, start worrying that that's going to be too big, that the column will either have too many plates, or it will need too much of a reflux ratio, or both. Okay, so that leads on to the second. Wait, I need a pointer. That leads on to the second point. The reboiler duty must not be excessive, and that is simply either you must use lots of plates, or you must have a high reflux ratio. And if there's a high reflux ratio, the reboiler duty will immediately increase. Right, the tower pressure does not cause the mixture to approach the critical temperature of the mixture. If you get to the critical temperature, then there is no separation. Then you just simply have that what do we call it, and neither a liquid nor a gas, a phase. And there's no separation.
Supercritical fluid.
Yes, that's it. Supercritical fluid, but it's there's a word for both a gas and a liquid, a fluid. It's a fluid, yes, correct. Okay, so next one is pressure drop must be tolerable, especially if the operation is under vacuum. Right, so I have talked about this. If you think of an ordinary distillation column and then a plate, to make it easy, a plate with 10 centimeters of water, 10 centimeters of liquid, will have a pressure drop of approximately 1 kPa. So as soon as you have 10 of these, you have 1 meter of water head from the bottom of the column to the top of the column. And with atmospheric distillation, that's fine. 10 kPa in 100 kPa is not a problem. But as soon as you have a vacuum distillation, something working at 0.1 kPa absolute, then there's a big difference in the absolute pressure at the bottom of the column compared to at the top of the column. And so generally, if you're going to be using, if you are going to be using vacuum distillation, you would prefer to have a packed column because then the vapors do not have to bubble through a head of liquid. They will simply be contacting on the surfaces of your packing. Okay, but most of these things, this whole list of requirements for an ordinary distillation, in most cases these are fine. That you would be able to use ordinary distillation. Right, the overhead vapor can be at least partially condensed at the column pressure to provide reflux without excessive refrigeration requirements. All right, so that's, if you think back to your test, you would need to refrigerate your ethylene so that you would have a reflux of ethylene. So you have to look at using your column pressure as high as possible, where you can still use a refrigerant with a single stage. And that would mean that it wouldn't be an excessive refrigeration requirement. And then if you have, for instance, oxygen or nitrogen that is dissolved in the feed as it comes in, that would be taken off as a small vapor stream off the top of the partial condenser. But the ethylene would be your product, and that would come out as liquid ethylene. The bottom temperature of the tower pressure is not so high that chemical decomposition occurs. Of course, the higher the pressure, the higher the temperature, especially at the reboiler. And at the reboiler, you must not get such a high temperature that you get chemical decomposition. Of course not. And azeotropes do not prevent the desired separation. So that is something we're going to go into in much more detail in later sessions when we look at residue curve maps. That'll help us to find suitable sequences of distillation columns where azeotropes are involved. Right, so as I said, most of these points can be met with the normal problem. So generally you'll find that the alpha is greater than 1.05, at least 1.1, and after that, most of these things will be true. Okay, let's go on to the next slide. Right, this is In previous lectures, I've told you that you should be trying to use a atmospheric column as long as you can use cooling water to cool down to condense the distillate product. This is a more general algorithm. Remember, we were talking about algorithmic methods versus heuristics. This is an algorithm, so let's go through the algorithm and see how it fits in with what we know at this stage, and especially in relation to the previous slide. So at the start, we know what separation we want. Okay. First, we calculate the bubble point of the distillate at 49 degrees C. If that bubble point, so in other words, 49 degrees C is we're using that temperature because then we could use cooling water as for the condenser. So if that pressure of the distillate is less than 14.8 bar, 1.48 megapascal, then you're fine. Then you would operate your column at that sort of pressure, and now you can estimate the bottom's pressure, and which would be very close to the distillate pressure, and you can calculate the bubble point temperature of the bottoms at that pressure. And as long as that temperature, TB, is not so great that you start getting decomposition of the bottoms product, then you're done. Then you have your distillation column. You've got its temperature, you've got its pressures, temperature at the top and the bottom of the column, you've got its pressure, and essentially you're fine. If that temperature is too high, then you would lower the pressure appropriately until you don't get decomposition. What that's going to do up here is it's going to lower the temperature of the distillate, and then you would have to use refrigeration. Right. If that pressure that you work out at 49 degrees C is greater than 215, greater than 15 megapascals, then you calculate the dew point of the distillate, and if that dew point is less than 25 megapascals, and just remember this sort of number, there 25 megapascals and 2.8 megapascals and 2.5 megapascals, 25 bar, 28 bar. That is the temperature at which many organic molecules are you're getting towards the critical point, the critical pressure. So that's why they're using this as a limit. So as long as you are below 25 bar or so, you can carry on and estimate the bottom's pressure and carry on in the normal way. If it's more than that, then you would need to go to a refrigerant. In other words, we were trying to use cooling water. If you couldn't, you'd need to go to a refrigerant at 28 bar pressure or 29 bar pressure. So keep that number in mind. That is approximately the highest pressure you'll ever operate a distillation column at. And then you can carry on with the normal thing, getting your distillation column. So there, instead of heuristics, here is a rule-based, in other words, an algorithm by which you can choose your separation traits. But it comes down to pretty much the same thing as I've been saying previously. You try and use atmospheric pressure distillation, and as long as you can use cooling water with atmospheric distillation, then that's exactly what you'd use. Okay, now let's have a look at the number of sequences for of P minus 1 ordinary distillation columns to produce P products. So if you've got 2 products that you need to produce, of course you need 1 distillation column, P minus 1 distillation columns. But when you've got 3 species, you'll need two separators, and there are 2 sequences in which you can put those 2 together. Similarly, as you go to 4 and 5, the number of sequences, of different sequences you can use, starts increasing according to this to the product of the number of species. Right, so let's have an example. If you've got a 4-component separation, A, B, C, D, this is the direct sequence. I mentioned this in class before, and you noticed that in the test, I'm sure. Direct sequence means you take off products as distillates one by one. So you'll take off A first, then you'll take off B, then you'll take off C, and then you'll, oh well, as soon as you take off C, you've got D coming off. Right, and then the opposite of that, indirect sequence, that you take off products one by one as bottoms products. So you take off D, then you'll take off C, then you'll take off B, and then automatically you'll have A as the distillate. So, oh wait, I just want to click there. And these are other separation sequences that are possible. First, take off A as a distillate, and then next take off D, and lastly BC. Next one, you separate right through the middle, AB and CD, and then you can separate those 2 separately. And then finally take off D first, and then you can do, after that, you can do the direct sequence, taking off A and B in sequence. So there you have it. For a 4-component separation, there are 5 different ways of doing ordinary distillation. Right. Oh. No, wait. I'm already on a class exercise. Right. These are the 6 heuristics that apply to identifying the best sequence using heuristics. So if you've got 5 components, for instance, we'll be doing a class example like that. You've got 5 components, you're going to have many different possible ways of doing that many combinations of sequences that you can choose from. And these heuristics have been put together simply to make it easier to reduce the number of reasonable answers that you can get as far as sequences go. Okay, so the first one, remove thermally unstable, or corrosive, or chemically reactive components early on in the sequence. Think back to when we made vinyl chloride monomer. One of our products was hydrogen chloride gas. Of course, that is corrosive, chemically reactive, and therefore we want to remove that early in the sequence. And we removed it first by using, I think it was 12 bar pressure, and then we used refrigeration. Right, the second, remove final products one by one as distillates, the direct sequence. Right, so I just want to go back to this first one. This first one is a strong heuristic. Yes, you always want to remove especially unstable or components that are a safety risk, poisonous, corrosive, chemically reactive, because corrosive would mean that you must make your distillation column out of special metals, and if you can remove it quickly, then the rest of the separation sequence is much cheaper. You can possibly use mild steel instead of a fancy stainless steel. All right, so let's go back to the next one. Remove final products one by one as distillates, the direct sequence. Now, think back to your test where I actually said you should remove, you should sequence your columns in the direct sequence. The reason is, if you remove the most volatile component, you use a higher pressure, and as soon as it is removed, think of the ethylene that you have to remove. That was at a high pressure. And as soon as you've removed it, then all of the columns could be operated as atmospheric columns in that particular example. So one by one as distillates is particularly some of the products are too volatile to remove at atmospheric pressure using cooling water. So it's also a fairly strong heuristic. Numbers 3 and 4 are probably stronger than number 2. So let's go to number 3. Sequence separation points to remove early in the sequence those components of greatest molar percentage in the feed. Right, so if you've got A, B, C, D, and D is a large molar percentage, you would want to remove that as quickly as possible. It might take you might be able to remove it immediately if it was A, B, C, D, or if C had the highest molar percentage, you would be able to remove it in the second distillation column, because you can remove C, D, and then you can remove C. So that is as quickly as possible. Right, and then this one is probably the first thing you think of if you don't think of, if heuristic 1 is not applicable, in many cases it's not. This is the first one you'd be looking at. Sequence separation points in the order of decreasing relative volatility, so that the most difficult splits are made in the absence of other components. Right, so there are two things. First, make the first separation with the easiest split, the highest relative volatility. And then eventually, that means that you will be doing the most difficult splits in the absence of other components. So you'll see the importance of this particular heuristic in the class example that we're going to be doing next. Right, finally, or number 5, sequence separation points to leave last those separations that give the highest purity products. Right, so this is a heuristic that's not often used. It's only if you say one of these products needs to be at 3 nines purity, in other words 99.99% purity, then you would want to leave that separation last. Okay, so this is not going to be applicable in our next example. Lastly, sequence separation points that favor near equimolar amounts of distillate and bottoms in each column, and that way the reboiler duty will not be excessive. So if you're taking a small amount of A off in your first column, then the reboiler duty would be excessive, because you need to reboil a lot of the liquid that you're making. So yeah, this is also a fairly important heuristic. So if we summarize, I would say that heuristics 3, 4, and 6 are the most important heuristics here. If one is, if you do have thermally unstable, corrosive, or chemically reactive components, sure, that would be important. But in most cases, it's not going to be important with heuristics 3, 4, and 6. Yep, right. Let's take questions. And we'll really, or whoever has raised their hand, you can switch on your audio and ask. There we go. I can hear somebody.
Hi, I wanted to ask, according to the sequences, which would you take for? Would you remove first? Okay, I understand one is not that important, but we also have 3 and 4 and 5, which kind of like plays along each other. So how would you label them as which one is the most important?
Yeah. Okay. So you've all been drilled with this thing of apples and oranges, units of measure, and obviously these things we haven't got units of measure. How can we compare direct sequence with greatest molar percentage? The units are different. So yeah, what we the reason that we've got this class test now is that, or this class exercise is so that we can get a feel for which are important. And yes, so it's a good question, and that's essentially what we're going to be addressing now. So let's go on to the exercise. So we've got propane, isobutane, normal butane, isopentane, and normal pentane. So obviously, when you've got a C3 and a C4, you've got a good alpha relative volatility. When you're trying to separate two isomers of C4, you've got a poor relative volatility. When you've got two different species, C4 and C5, it's a relatively good relative volatility, and when you're separating the two C5s, it's a poor relative volatility. So those are the relative volatilities, and then what's also important is the molar flow rate of each of these components. So we've got propane, isobutane, and there you can see that one of the biggest flow rates is the N-pentane. So essentially what I'd like you to do is to take 10 minutes, time it from now, and see what sequence you can come up with based on these two bits of information: the species, the species flow rates, and the alphas, the relative volatilities. You can see that the purity required is about the same for all of these components, so that heuristic number 5 is not going to be relevant. And all of these are just normal. They are normal hydrocarbons, so heuristic 1 is not going to be important. All right, let's go on to the next slide, where I have put all of the heuristics on the page together with the flow rates and the alphas. And you can start, just get a piece of paper, each of you just get a piece of paper and start sketching out the sequence that you think you would take to solve this problem. So this is the type of question I give often in the second semester test, where I give exactly this sort of information, and I say choose a sequence of distillation based on this data. You're welcome to chip in if you'd like to ask some questions while you're going through this problem. Yeah, Yakalui.
So the thing about the largest molar percentage of the feed, can you kind of expand that to splitting streams into the smallest possible side streams so that you don't have one massive stream going along, because that implies bigger columns. So if you can like halve the total amount into two separate streams, you have a series of smaller columns. Is that the reasoning behind splitting it early, the large amounts?
That's correct. So in this case, you can see there's up here, that split here, N-butane, NC4, and IC5. We would have 500 at the bottom and therefore 400 at the top of the column, and so that would really suit that heuristic number number 3. No, that's
both number 3 and number 6.
It's number 6. It's number 6. So that's particularly number 6. The highest one is N-pentane. So it is. So doing that separation is more to do with heuristic 6 than to do with heuristic 4. But it does help because, yes, if you wanted to remove N-pentane first, then
it's a difficult split.
It's a difficult split. So in this case, heuristic 4, heuristic 3 is not going to be very useful.
Okay, yeah.
Because that's a difficult split. So, but certainly to do the very first split over here between NC4 and IC5 does make a lot of sense.
Okay, cool.
Yes, Shana. Remember to switch off your mute if you want to speak, Shana.
Is it on now?
Yes, I can hear you.
Okay, sorry. When we split the NC4 and IC5, is it reasonable to assume that, let's say, everything above, where we look at the relative volatilities, will everything above NC4 split actually above, or how do we know that the C3 won't go up and then the, let's say, IC5?
Okay, so
do you understand my question?
I'm pretty sure I do. Whenever we list components, we're going to be listing them from top to bottom as most volatile at the top, least volatile at the bottom. So remember when you did mass transfer, there was this thing of a heavy key and a light key. So if we look at this distillation over here between NC4 and IC5, the light key is going to be the NC4, and the heavy key is going to be the IC4. And so you'll design your distillation column that you make a clean separation between those two. Automatically, because IC4 is more volatile than NC4, and C3 is much more volatile than any of those two, automatically they will be at the top of the distillation column. They will come out as distillate. If you make that separation there, you've got the light key and everything lighter than that will come out at the top. The heavy key and everything heavier than that will come out at the bottom. So that's a really important question you've asked. It's critical. Oh yes, let me just carry on answering that question further. Is you can also see that from the relative volatilities, because there C3 over C4 is a number greater than 1. So in this subject, we are always going to be listing things from the most volatile down to the least volatile, and therefore the relative volatility will always be a number that is greater than 1. So because these are all greater than 1, as we move down here, it also means that this is the most volatile compared to this, compared to this, compared to this, compared to that one. Okay, there was somebody else who wanted to ask a question. Yes. Gabriela.
I was also just going to ask if we should have changed the relative volatility to have the same reference component. But you kind of answered my question by explaining that you left it from the most to the top.
Yes, it's more useful having the ones that are in sequence volatility wise, because that is ultimately where you're going to do a separation. So if you look at C3 versus IC4, at one stage you will need to do a separation at that point, and so it makes more sense that you should do it there.
Okay, thank you.
Or it makes more sense that you should be talking about the 3.6, or instead of C3 versus NC4, which will be 3.6 times 1.5. Yeah. Okay, let's move on and have a look at the answer that was given in the textbook. And you'll see the answer in the textbook does something different to what we were suggesting. Now, we were saying let's separate NC4 from the C5s, because then we'd have that heuristic number 6 applying. We get equal molar things. In this case, they were saying, well, C3, there are 2 heuristics that apply, and the one is direct sequence. The other one is it is the easiest separation to do. Let's just go back. Gabriela, would you like to, or have you answered your question already? Okay. So yes, it does make sense. And now you'll see we're coming to something that might be that I'm going to suggest to you, that when you're choosing a sequence like this, if you simply choose the most number of heuristics that apply, rather than which one is more important than another one, then perhaps you're going to get to the right answer as reliably as any other. So when I ask a question like this in the test, I want you to label these columns as column 1, column 2, column 3, column 4. And then you can say column 1, we've got 2 heuristics that apply. In column 1, it's going to be that we're using direct sequence and we're using the greatest relative volatility for this column. So there are 2 sequences that work. Yes, Jared.
So surely this almost directly contradicts heuristic 6 though, because C3 was an incredibly low flow rate, whereas so you're splitting a huge amount of flow down to the bottoms product.
Yeah, it does. And my personal preference is in fact the C4 to C5 split as the first one, because you still get 2 heuristics that are applying. The one is equal molar flow, and the other one is, it's not quite the easiest separation that you want to do first, but it is darn close. You know, it was 2 points. Let me just move my slides. I can see what it was. 3.6 versus 2.8. Both are easy separations, so you might as well just do that easy separation there. So yeah, these questions are somewhat open-ended. Although when I asked them in the exam, exams and tests, I try to make them fairly straightforward and easy to see what the correct answer would be. Otherwise, it's more difficult to mark, of course. Yeah. All right. There was a comment that you said there. Yeah, speak. Okay. All right. So let's go on. So,
Prof,
yes.
the comment was a notification for a question in the chat, a text question.
Yes. All right. Let me go and have a look. Heuristic 6 is equal tops and bottoms. Please explain heuristic 6 again. Yeah. All right. If we do, I'm going to go back to this thing, and we look at heuristic 6. Sequence separation points at favor near equimolar amounts of distillate and bottoms in each column. The reboiler duty is not excessive if you do that. Right. Let's say that you do what they suggest right at the beginning, and you're separating propane from the rest. You will have 850 or so kilomoles per hour coming out at the bottom of the column. Now, to get any separation in that bottom part of the column, you would need to have a reboiler, a ratio of vapor coming up counterflow to all of these 850 kilomoles per hour that are coming out the bottom of the column. And therefore, you would tend to have quite a high cost of the reboiler. Now, remember, reboiler, that's the expensive bit, because you need to use energy to get the steam to run your reboiler. A condenser, we say we're always trying to use a condenser that we can use cooling water, and cooling water is cheap per kilowatt, because as soon as you heat up your cooling water, you put it into a cooling tower, and you really use very little energy to cool down that water in the cooling tower. So yes, that's why we'll always be considering the reboiler duty as the important one, because that's where we actually spend money on energy. Yeah, so that's pretty much why we would prefer to have equimolar amounts, because then we would be condensing just as much as we are reboiling. You might have seen pictures of columns, distillation columns, where you've got the bottom part of the column as a very broad column, and the top half is a thin thing sticking out the top, and the feed is where those two diameters meet. Of course, that also adds to the cost of the column to have to do the diameter. So that's pretty much where heuristic 6 comes from. Okay, I want to go back to my share files. Now sharing. Okay, I'm back on my slides. Okay, so if we obviously they've taken as the second column, they've taken the out of these 4 components, that would certainly be the easiest separation, and it would be an equal molar separation. So again, there are 2 heuristics that would apply for column number 2. So if you label this column number 2, you'd be able to list those 2 heuristics as valid heuristics for that column. And then finally, the last 2 separations that are left are going to be the most difficult separations. So I'll just go back to our problem thing, and there we've got 1.35 and 1.5, the 2 most difficult separations we're doing last. And that is heuristic number 4, so that the most of splits are made in the absence of other components. Okay, so that's pretty much the class example, and it gives you an idea. you can see the two sequences. If we chose what I suggested, let me start drawing what I was suggesting. We had that, and then we had, and this would be
Sorry, sir. Might the whiteboard not be easier to do bit bigger space?
yes, it would be. I'm worried about getting back to this presentation if I use the whiteboard, so I think we'll have enough space anyway. ABC/CD for this particular separation. So we'll have CD at the bottom, and then we would be doing CD. Let me just draw in that one. No, that one, text, shapes. Oh, shapes. There's our CD separation, and that is one of the most difficult. So that would be last, because that's all we need. Then we'll have ABC at the top here. ABC, and it is clear that we would want to do then it is clear that we want to take off A next, because the AB is an easy separation. And finally, we would be left with a BC separation as the last one, and that again is heuristic 4, where we're trying to do the most difficult separation. That one was CD. Oh wait, I've got something wrong here. It's a DE. This is more confusing to you than I. How do I delete that one? Oh, geez, if I delete everything, never mind. This is ABC/DE. And this separation here will be taking off A, which is direct sequence, and it is the easiest separation to do. And so yes, these two answers that we've got here, the one in yellow or this one in black, they're pretty much equal. And if you count up the number of heuristics that are involved in each of these answers, you'll find that they're probably the same. Right, we're getting to the end of our lecture. Damn. All right, so we'll carry on with this at the next lecture. I'll stop the recording and I'll see you tomorrow. Thanks everybody for attending. So far so good. Glad to see a smiling face. See you tomorrow at 11:30.